Greetings, ladies and gents, and welcome back at Semi Maths and Science Club. In this video, we'll be looking at an extended practice question. So, in this case, remember in the previous lesson, we looked at energy. So, in the first lesson, which was lesson 1, we looked at work. In the second lesson, we looked at energy, and we covered quite a lot in this section. So in this case, this video is it's actually dedicated to what we did in the previous lesson. So if you haven't watched that video, be sure to refer back to it. I'm simply just gonna leave a link in the comment section to that video there, because we covered a lot of work. So I would actually suggest that you watch that video before you even watch this, so that it's not confusing. All right, now if you have any question, ladies and gentlemen, that you would like to ask, or if you have any topic that you would like me to cover next, be sure to throw that in the comment section, and I'll make sure that I cover whatever topic that you would like me to cover. Even if you want me to to constantly go through a lot of past papers, right, suggest that, and I'll do that as soon as possible, whether being in maths or physics. Right, unfortunately, those are the only subjects that I'm able to cover. The rest is history. So in this case, if you haven't, of course, subscribe or follow, be sure to do that, and also hit that notification bell, so that when the rest of the other videos comes, you'll be the first to be notified. Now, remember, I said that in this case there are four extended practice questions. So in this case, there would actually be 4 videos to follow. So there are 4 videos only on this extended practice question. So watch out for that. So in this case, for question 1, they say that a slide PQR at an amusement park consists of a curved frictionless section PQ and a section QR which is rough. Right, this so in this case they're telling us that in this case this surface, right, it's actually a curved surface. I don't know. I don't know why I'm pronouncing that word in that way. I don't know if that's how it is pronounced or not. I don't know. It's just like it feels weird, like curved. What am I saying? Jesus help me. I mean, like, what the hell? But anyway, forgive me, ladies and gentlemen. My English has its own way of of disappointing me at some extent. So they're telling us that in this case PQ is a curved surface, right? In this case, they say that in this case. So in this case, we also have in this case QR, which is a rough, right, a rough straight and inclined 30 degrees to the horizontal. So in this case, they're telling us that this surface is actually a rough surface. So meaning that in this case, we have friction on that part there between point Q and R. They say that the starting point P, right, that point P there, right, is 3 meter above point, in this case above point Q. So in this case, they're saying that that point Q, that point P, is actually 3 meter above that point Q. As in this case, they're actually giving us in this case the vertical height between these points. All right. So in this case, they also say that in this case the straight line section QR is 5 meter long. Right. They said that a learner with mass of 50 kg starting from rest point P. They say that. So in this case, we know that that word there, rest, simply mean that in this case that that person there is busy resting, there is not moving, right? So in this case, we know that of course the speed of that person at the point P is simply 0. So they said that learner there slides down section PQ, then continues down the straight section, which is QR. So they said that state the law of conservation of mechanical energy in words. We know that of course the law of conservation of mechanical energy in words simply states that in an isolated system, the sum of the potential energy and kinetic energy of this of an object is conserved. So in this case, so that's the principle of conservation of mechanical energy. So it says in an isolated system, the mechanical energy is conserved. Or we can say that in an isolated system, the sum of the potential energy and kinetic energy is conserved. So you can put it in that way, and you can get those 2 marks. So in this case, for 1.2, so in this case, what you must just notice that this section PQ is actually a frictionless surface. So we can actually use the principle of conservation of mechanical energy on that section there, right? Because we do not have applied force, do not have frictional force, no tension or air resistance there. As in this case, they say that for 1.2, calculate the speed of the learner at Q, right, at that point there. So in this case, since we know that of course that learner started from this point, and we know that of course this is actually a frictionless surface, right? So we can actually use the mechanical energy there. So in this case, what we are simply going to do would be to say that in this case, the mechanical energy at point P, simply equal to the mechanical energy at point Q. So in this case, if we expand this, so simply become in this case mgh at point P plus in this case a half multiplied by the mass multiplied by the speed squared at point P. Remember that the mechanical energy, we know that that's actually the sum of the object's kinetic energy plus its potential energy there, which is what we have there. So in this case, simply be equal to the mechanical energy of the object at point Q. So simply be mass multiplied by, let me just do that. So simply be mass multiplied by the gravitational acceleration at point Q plus in this case a half multiplied by the mass, in this case multiplied by the speed squared at point Q there. So if we substitute our values, so in this case we know that of course the mass is simply that 50, so be 50 multiplied by 9.8 multiplied by the vertical height. We know that of course point P simply 3 meters above that the point Q there. So in this case, you take that point Q as your zero reference only for this section here. So in this case, when our object is at that point, so it simply be in this case, it would be at that zero. It would be at our reference point which would be in this case 0. So in this case, simply be equal. So simply be in this case 3 at multiplied plus a half multiplied by the mass, which is 50, multiplied by the velocity at point P, which is simply 0, but to square that, since it simply be equal to the mass, which is 50. But now remember, we are now at point Q, so it simply be multiplied by 9.8 multiplied by 0. All right, why? Because in this case, this is a kind of our resting point, but in this case for this section here, so in this case when our object is at that point Q, in this case it would be in this case, so it would be it would not be elevated in this case any units above that point there, so it simply be 0 there. So simply be plus a half multiplied by 50 multiplied by the speed at point Q there, which is what we are looking for. Now these two, all right, simply going to give us a bunch of zeros. All right, so in this case you can just neglect those two there. So in this case you can just simply neglect those. So in this case, if you put this into your calculator, what you're simply going to get is actually 174, right, point it's actually 1740 being equal to in this case, so remember that a half multiplied by 50, so it's actually going to get 25 multiplied by the velocity at point Q squared. So in this case we divide by 25 on both sides. So if we do that, what you're simply going to get is 58.8 being equals to V point Q squared. And what we do, we take this case square root. Remember that we are just simply looking for speed there. So in this case, if you put this into a calculator, what you're simply going to get would be your V, your speed at point Q to be in this case 7.67 if you round that off meters per second. So that would be in this case your speed for that of the object when it reaches that point Q there. So you must just keep that. So in this case, that's the speed that we are going to use when our object reaches that point Q there. So when it reaches that point Q, we know that it would be traveling with a speed of 7.67 meters per second. So in this case, for 1.3, they said that draw a labeled free body diagram for the learner while he or she is on section QR. They say that's for 3 marks. So in this case, while this learner, I almost said object. So while this learner is on that section QR, in this case, she is experiencing a frictional force. So in this case, remember, if we were to draw a free body diagram of that learner at that point, in this case, we'd actually have our inclined there, like that. So in this case, so we'd actually have now our force of gravity being vertically downwards. We have in this case our frictional force, which is always acting in this case which is always opposing the motion, right? So in this case it would simply be Fk. And we also have in this case our normal force, which is which would be perpendicular to our surface. So this would be the free body diagram that you would give them if they ask for a free body diagram. But for you, in this case, you would need to draw the one with components. So in this case, if they ask for a free body diagram, this is for them, right? So in this case, this would be in this case for you, right? So in this case, please do not write that this is for them, right? Don't do that. So in this case, this simply be in this case for your calculations, as it makes things a little bit simpler. So in this case, what we are simply going to do would be to draw a second one, but this is for us. So in this case, we would need to resolve that Fg there. So in this case, they have in this case Fk, but in this case, we also have in this case our normal force. Now remember that in this case we have in this case we had our Fg being in that direction there. It wasn't on this dimension or on that dimension. So in this case, when we resolve that that Fg there, we are actually going to have in this case our Fg parallel, which would always be in this case down the incline. Just write that using another color. So we'd actually have our Fg parallel being down the incline, and would actually have in this case our Fg perpendicular would be in this case, which would be in this case perpendicular to our surface. Now remember, to calculate Fg parallel, we say that in this case we'll say that mg multiplied by in this case by sine of the angle, right, of the inclination, which I'm simply going to call that to be beta, right? So in this case, to calculate in this case Fg perpendicular, so simply be equal to in this case to mg multiplied by the cos of the angle of inclination, which I'm going to call, which would be beta in this case. Right? The reason why I'm not using theta is that I don't want you to be, to kind of to mix it up with that data that we use in the work done formulae, right? So in this case, this diagram is for us. We are going to use that later on in case if we need it. So they said that the coefficient of kinetic friction, which is that between the learner and the surface, QR is actually 0.8. So they actually gave us that coefficient of kinetic friction. So they said that calculate the magnitude of the kinetic frictional force acting on the learner while the learner is on section QR. Now remember that to calculate the frictional force, we said that in this case Fk is actually equal to mu, right, multiply that by the normal force. Now how do you get the normal force? Now remember that in this case, since we are actually on this inclined, right, so we know that in this case our normal force there is actually equal to that Fg, in this case that Fg perpendicular there. So in this case our normal force would simply be equal to, in this case, to our Fg, in this case perpendicular, which is simply be equal to mg multiplied by this case by cos of beta, which is simply be equal to this case, which is the mass, which is let me see. So we said that mass, that's 50, multiply that by 9.8, multiplied by the cos of 30 degrees. So this will be 30 degrees. Now I'm simply not going to put that into the calculator. Why? Because it will give me a recurring number, which is actually 436, right, 593 blah blah blah. But I'm simply not going to round it off. Why? Because that's not actually the final answer. I'm just going to actually reserve that there. So in this case, what I'm simply going to do is that instead of normal force of that end there, I'm simply going to replace it with that. So in this case, simply be equal to, in this case, 0.8 multiplied by, in this case, 50 times 9.8 times by cos of 30 degrees. So in this case, if you put that into a calculator, what you're simply going to get would be, in this case, 34.93 Newton. Right, so in this case, we know that, of course, the SI units for kinetic friction for force is simply in Newton. So in this case, for 1.5, they said that use energy principles to calculate the work, to calculate the speed of the learner at point R. Now, let me just go borrow our energy principle formula there that we used last time. So in this case, let me just put them there. All right. So in this case, they said that you use energy principles to calculate the speed of the learner at point R. Now remember that we cannot use now the mechanical energy at 8 point at this section. Why? Because in this case now we actually have non-conservative forces there. We have external forces there. So in this case, the only formula that we can actually use would be this 2. But remember that we on this section here we do not actually have that vertical height here. We do not have that vertical height. It's not given. So in this case, this is not going to work. Why? Because in this case, that potential energy there, it would actually require us to use that H there, which we do not have. So in this case, the one that actually work better would be in this case this one, which says that W net is equals to the change of the object's kinetic energy. But remember that the W net is simply the sum of all the forces. So this simply be the sum of all the work done on the object by all the forces that we have. So in this case, we are going to say that in this case, W net simply be equal to the object's change in kinetic energy. So remember what we know that, of course, remember that in this case, on this surface that we have in this case, we have the normal force, we have the gravitational force, we have in this case Fg parallel, also have in this case Fk there. So in this case, this will simply be equal to the work done by in this case by Fk plus work done by in this case by Fg parallel plus work done by so this is by Fg perpendicular plus in this case work done by in this case by the normal force, which is Fn. So it's simply be equal to in this case it's be equal to half mv squared in this case final at point R minus in this case half mv squared at point Q. So it's final minus in this case initial. So in this case, and remember that of course there are two ways that we can use to calculate that. We can first calculate F net and then you just simply use that. So in this case, what I'm simply going to do there, remember that there's 2 are simply going to give us a bunch of zeros. Remember that of course work done by a force that is perpendicular to your surface is simply 0. So in this case, we only need to calculate the work done by those two forces there. So in this case, what we are simply going to do would be to say this is force so multiplied. So in this case, remember that work done is simply force multiplied by the displacement multiplied by the cosine of the angle between the direction of the displacement and the direction of the force in question. So this will be multiplied by cos theta plus in this case Fg parallel multiplied by the displacement multiplied by the cos of theta. So simply be equals to half multiplied by the mass multiplied by the velocity squared at point R minus a half in this case mass multiplied by the speed squared at point Q. So in this case, what we can now do is to substitute our values. So in this case, we know that our Fk, that's actually 34.93. This is 34.93 multiplied by the magnitude of our displacement, which is 5. But in this case, we say the cos of. Remember that theta there is simply the direction between the direction of the displacement. So in this case, we know that in this case our object was displaced in this case downwards. So in this case, we know that in this case our Fk would be in this case in that opposite direction there. So in this case, that theta is simply the angle between our Fk and in this case our displacement, which would be in this case 180. So simply be cos of 180 plus our Fg. Also remember that in this case our Fg parallel, we said that we calculated by saying Fg parallel is equal to mg multiplied by sine of beta. So this simply be equal to mass, which is 50 multiplied by in this case by so in this case multiplied by 9.8 multiply that by in this case by the graph multiply by the let's say multiply by the sine of the angle of inclination, which is 30. So in this case, this simply be in this case your Fg parallel, but we multiply that by the displacement, which is 5 multiply that by the cos of. Remember that in this case again the theta there, remember that in this case our Fg parallel is actually in the same direction as our displacement. So in this case the angle between them would simply be in this case a 0. So in this case you say equals to a half multiplied by the mass, which is 50, multiplied by the speed at point Q, at point R, which is what we want. So this will be VR squared, right? V squared, and this is minus a half multiplied by the mass, which is 50, multiplied by the velocity, by the speed of the object at point Q, which we found to be 7.67. This is 7.67. There you can use that. We square that. Now if you put this, now remember that, so if you put this, all right, into your calculator, what you're simply going to get is 9. All right, let me just, so this is going to be, in this case, 937.62, the 6267, blah blah blah. I'm not going to round that off early. Now in this case, what I'm simply going to do, so if you put this into your calculators, in this case, what you're simply going to get, now first, so if I take half multiplied by 50, I'm actually going to get, in this case, a 25 VR squared. This case, if you put this into your calculator, what you're simply going to get is actually negative 1470 at 0.2, that's actually 0.7225 there. So in this case, what I'm simply going to do would be to take this to the other side. Now we can't round off early. Why? Because in this case, this is not the final answer. So in this case, what we are simply going to do, if you take this to the other side and you add it, so in this case, when it goes to the other side, it changes signs, so it simply become now 2,408.34, 34922, so on and so forth, simply be equal to 25 multiplied by, in this case, V squared at that point R. So what you now do would be to divide that by 25, divide both sides by 25, so this cancels with that. So in this case, what I'm simply going to do would be to take the square root, all right, in this case on both sides. So in this case, remember that if I divide those two, these two are gone, so these two here disappear. So in this case, what I'm going to do there would be just to take, in this case, my square root, right? If you put that under the square root, now remember that, put that whole thing there. So in this case, your V at point R simply be equal to, in this case, so simply be equal to 9.81 if you round that off, meters per second. So this is simply be, in this case, your answer, right? So I would not suggest that in this case you round off early, so you must keep those, because in this case, when you take a square root, I think your answer would actually kind of, change drastically. So in this case, this will simply be it for this question. Now there's another question to follow again, so this would be the second one, but we'll cover it in the video to come. Now if this video helped you at some extent, be sure to leave a like. If you've got any question, again, you're more than welcome to leave. You're more than welcome, in this case, if you have any topic that you'd like me to cover, you're more than welcome to throw that in the comment section, right? Of course, if you have any questions, or if you've got of course, if you want me to cover, maybe past papers, a lot of past papers, throw that in the comment section. I'm always reading those. But otherwise, ladies and gentlemen, as the story always ends, this is Sir Mike signing out. Sharp sharp.